In this presentation, we will be talking about the usage of formal methods in industrial applications. So first, what are formal methods? There are several definitions out there, but according to NASA Langley, formal methods are mathematically rigorous techniques and tools for the specification, design, and verification of software and hardware systems. So what is the value of formal methods? Well, once a system has been defined using formal methods, the logic of the system can be proven to produce an expected result. And naturally, this requires a proper formal definition of a system, which requires converting the system's specification or code into formal mathematical logic statements. The use of formal methods can be particularly useful during many phases of the system development. So during specification, the utilization of formal methods can reveal missing system requirements. It can also help a system designer think through the various states that the system should contain and when those states should be entered or exited. Formal methods also have tremendous value during the design phase. While system requirements written in natural language may be interpreted differently by different people, a system defined using formal methods can only be interpreted a single way. Additionally, several tools exist that convert a system specification defined using formal methods into actual source code, saving development time and cost, and giving more confidence that the system is actually designed according to the spec. And finally, formal methods allow a system's expected state behavior and the whole system state space to be checked and verified using logic. And this is one of the biggest benefits of using formal methods, especially for systems where safety is critical, such as the airline industry, elevator industry, medical field, etc. So in this presentation, we're going to look at how formal methods benefit industrial applications. So first, what is industry? Lexico defines industry as economic activity concerned with the processing of raw materials and manufacture of goods in factories. And some examples of industries that fit this definition include the automobile industry or steel industry. And the word industry can also be defined as a distinct group of productive or profit-making enterprises, which is the way that Merriam-Webster defines it. And this definition better fits industries like the airline industry or the healthcare industry. So formal methods are naturally useful in industry, as basically all forms of industry have pretty stringent requirements for safety and reliability. And at the heart of these industries, you'll often find industrial automation systems, which are highly distributed systems containing software to control mechatronic components that interact with physical processes. And a good example of an industrial automation system is pictured to the right. You can see the robot welders there, and those are used extensively in the automotive industry, and for good reason. They can generate welds that from one car to the next are identical. And when it comes to things like welds in an automobile, a good weld can be the difference between a survivable crash and a deadly crash. So when it comes to safety critical systems like this, formal methods really shine as they can be used to verify that a system will perform as expected. And at the heart of most industrial automation systems are what are known as programmable logic controllers, or PLCs. And a PLC is typically what's behind something like a robotic welder. So in this discussion, this presentation, you'll see lots of discussion on PLCs. So while the application of formal methods to industrial systems is certainly more popular now than it was 30 years ago, formal methods have been used in the past, certainly, and they're nothing new. In fact, they've been used for centuries to prove the behavior of mechanical systems. But recently, formal methods have started gaining usage in software-based systems, and this is the case as software is playing a much larger part in controlling how hardware systems behave. And one well-known study of the application of formal methods to software-based systems took place in 1995. The study was sponsored by NASA and Rockwell Collins, and it applied formal methods to a custom microcontroller made by Rockwell Collins to verify that a program running on the microcontroller would behave exactly as expected. And in this study, the researchers modeled the processor at the register transfer level and also at the instruction set level. And the goal was to trace each software instruction through the hardware to guarantee that the system would behave as expected. They found that formal methods are valuable even when applied solely to system specifications. And they came to this conclusion after discovering two errors in the software on their processor after simply using formal methods in the specification process. They also found that their engineers, who were not formal methods experts, could be trained to read and write formal specifications. So that was a study I'm going to refer back to, and it happened in '95. And so since then, lots of research has been done in the area of applying formal methods to industrial systems. And we're going to look now at some current systems and some current formal methods-based tools that are currently directed at industry. And as PLCs, like I mentioned, are at the heart of most industrial systems, a lot of work has been done applying formal methods to the systems that use them. And lots of work has been put into the development of tools that can automate the process of verifying the software that runs on PLCs. So one of the big benefits of a tool that can automatically verify a system's code is that the people who use those tools don't need to understand the intricacies of formal methods. They can simply be trained to input things like PLC code, which they are familiar with, and specify the desired system of the system behavior, and the tool can be used and can implement formal methods to perform model checking. And one tool that does this is called PLC Verify. That tool is currently being used at CERN to perform model checking on the PLCs that run a lot of the subsystems in CERN. And one study that was done using PLC Verify at CERN reported that the tool had already successfully been used to discover errors that were present in already well-tested PLC programs. And in this study, while I found that the tool could be used to reduce the time it took to perform model checking, it could not be used to model all system functions. And also, as the system is designed to take in PLC code, it's not intended to verify the system at the requirements level. So it certainly has some benefits, but in order to span the gap really between requirements and system verification, further expertise is needed in the area of formal methods. So that's one example. Another example of formal methods being used today in industry is formal methods being applied for recertifying legacy systems. So all over the world, new safety requirements are constantly being imposed on industry. And these new requirements are often imposed for the good of people, sometimes for the environment. And the infrastructure that currently exists in industry is very expensive. So when new requirements are imposed, it's often not possible economically to completely replace a legacy system with one that has already been certified. It's often much more cost-effective to update the software that controls the legacy system and then recertify the whole system with the new software. But while the cost of recertifying a system might only be a fraction of the system cost as a whole, the cost of recertification can still be high, which has led to the development of frameworks that automate as much of the recertification or the verification process as possible. One of these frameworks has been tested by a set of researchers, Thrombolidis et al. In his paper, Towards an Automated Verification Process for Industrial Safety Applications. And an interesting thing about the process proposed by the author and his team is that they are not taking PLC code as an input to their verifier, as was the case with PLC Verify, but they're actually taking as inputs PLC system models themselves. And in this framework, PLC models are developed using PLC Open XML standards, and then those models are automatically converted into UPAL models, where formal verification is then performed to recertify systems to updated safety standards. So while this process requires PLC models to exist, the fact that they can automatically be converted into UPAL models uh, where, where formal models can be easily applied makes this framework very valuable. So one of the other current ways that formal methods are being used, the PLC Verify tool we looked at a couple of slides ago, as well as the framework I just discussed, both model the controller primarily. And so given certain inputs, will the controller provide the expected output? However, some work is also underway to model not only the controller, but also the plant as well. And in this paradigm, both models, so both the controller model and the plant model, are then combined in a closed loop system as seen in the picture to the right. And when the system as a whole is modeled this way, formal methods can be brought to bear on the entire system. In the diagram to the right, you can see how the models were developed. So the plant model was developed using UML diagrams that detail the plant as a whole, and the controller model was generated using source code. And then, utilizing the system requirements for the system as a whole, formal methods were used to perform model checking on this combined system. So using the combination plant controller model has many benefits over simply modeling a controller and testing it against specific inputs. So first, when the plant is modeled, it should be modeled independently from the controller. And having an independent model like this often leads to discovering problems that would present themselves in the real world but may not have been taken into account when the controller model's various states were tested and verified. And another benefit of having an independent plant model is that if it's truly independent in the way that it models the plant, the same model can be reused with multiple different controller models with minimal modification. So if a different controller model were made, you could marry this plant model with a different controller model and reuse that same plant model. So the last slides were just a small snippet of the work that is currently being done in applying formal methods to industrial systems. But as a whole, how many deployed industrial systems today utilized formal methods at some point in the software development lifecycle? Well, several IEEE members recently joined forces to try to answer this very question. They performed a survey of all the major industrial publications to determine not only all the major industrial journals, rather, to determine not only whether formal methods are being used, but also the level of maturity of the systems that utilized formal methods in the publications that they found. So to gauge the maturity of those systems, they classified the systems using a TRL number, where TRL stands for Technology Readiness Level. And the higher the TRL number, the more mature and robust the system. So where a TRL 1 would indicate that a system has just been used to demonstrate the basic principles of functionality, TRL 9 would indicate that the system has been validated in a relevant environment but not demonstrated in a relevant environment. And then TRL 9, the highest level, indicates that the system has been proven in an operational environment. And just to give an idea of one system, the TRL level of the AAMP5 processor that I mentioned earlier that was tested in 1995 is a TRL 9 level system, so the highest level. And that indicates that the system has been proven, and again, in an operational environment. And so in the case of the AAMP family of processors, they're used in things like the display systems of Boeing 7 series passenger airplanes. So after surveying all the publications they could find on recent usage of formal methods in industry, what the authors of the study found was a bit surprising. So the majority of the publications were not applying formal methods to mature, proven high TRL systems, but to low TRL 3 through 6 level systems. And the authors cite several reasons why they believe this to be the case. So first, they say that the methods and tools that use formal methods require a high learning curve and expert skill sets. They also pointed out that the more mature a system is, the more complex it is, and therefore the more difficult it is to model. They also cited a lack of tools in the industry and industrial environment that utilize formal methods. And one other thing to note is that the authors of this study are not strangers to industrial systems or formal methods. They all have PhDs in relevant fields and decades of relevant experience. So they know what they're talking about. And in addition to characterizing the TRL level of surveyed systems, the survey also included the phase or phases of the software cycle in which formal methods were used. And so not surprisingly, among the publications surveyed, formal methods were applied during the testing phase more so than any other phase. And by testing, I mean to include test generation, simulation, and formal verification. And I say that it's not surprising because guaranteeing safety or reliability, or in other words, guaranteeing that the system will function as expected, often comes down to testing. And so while this phase is the one that most heavily utilizes formal methods, still other phases can still benefit from formal methods from a cost standpoint as well as a dependability and safety standpoint. And that's the reason because the system may function as desired, but if the requirements are not properly converted into formal methods, the system may leave out important requirements that could have been discovered during the process of converting the natural language requirements into a formal model. Also, the development phase can greatly benefit from formal methods because changes are much cheaper to fix during development rather than after deployment. So given that formal methods are not as widespread in industry, in industrial systems specifically as they could be and should be, what are some things that need to change for them to become more widespread? Well, first, if the usage of formal methods was standardized in all phases of the software development lifecycle, it would increase the number of people with skills in formal methods. And in my opinion, given my 10 years in industry, the lack of people in industry with proper training in formal methods is one of the main reasons it's not more widespread. But for the use of formal methods to be standardized, the domain-specific knowledge across industrial automation systems, it needs to become more formalized itself. Second, for formal methods to become more adopted in industry, the tools that support formal methods should be able to support more phases of the development lifecycle. So currently tools only support maybe a single phase or two phases, like the design phase or just the verification phase. And for tools to play better in all of these phases, more formalization is needed in the transformations between different modeling frameworks. Third, and this is somewhat similar to the need for more people with experience, domain experts in particular should be trained to master formal methods. So in order for meaningful productivity to occur, the same person must have a good understanding of the system domain from a technical perspective and have a good understanding of formal methods. Fourth and finally, more empirical testing should be performed in industrial settings to determine what forms of formal methods are most effective. So rather than simply proposing formal methods to solve problems, we need to implement and actually use the systems designed using formal methods, and then evaluate the design process and the outcome of the system while it's operating in a real-world environment. And so that summarizes my presentation on the usage of formal methods in industry. Hopefully it was helpful. And here are my references. Since this is a video, you'll have to pause the video if you did want to look up some of these references, but they were very helpful.